Hello everyone. So today we as a group are here to present you on Gray to Binary Converter Mini project. So this video would be presented by myself, Brinda, Bhavani, Bhagyashree and Anpurneshwari. So let's get started with the introduction. The objective of this project is to design and implement a gray to binary code converter using the Verilog. Gray code, also known as reflected binary code, is a binary numeral system where consecutive values differ by 1 byte. The converter transforms gray code inputs into standard binary code, facilitating compatibility with digital systems and applications. Significance of this project. Digital system integration. The gray to binary code is a fundamental concept in the digital system, enabling the seamless integration of binary code inputs into various applications. Communication systems. Gray code is commonly used in communication systems to minimize errors during signal transactions. The converter allows for easy interfacing with digital communication protocols. Counter and encoder design. In applications such as rotary encoders and counters, gray code is prevalent. The converter facilitates to use a standard binary representation in these systems. Educational value. This project serves as an educational tool for learners in the field of digital design and Verilog programming, offering hands-on experience in implementing a crucial digital logical operation. Understanding and implementing a binary to gray to binary code converter is essential when dealing with systems that utilize gray code and input devices but require binary representation for future processing and control within a digital system.
The methodologies are: problem specification clearly defines the problem. Create a specification document outlining the requirements and constraints for the gray to binary code converter. System architecture. Determine the system architecture. Decide on the overall structure and the functionality of the converter. In this case, a combinational logical circuit is typically used. Bitwidth specification. Define the bitwidth. Decide on the number of bits for both the gray code input and binary code output. This will guide your design and test bench creation. Truth table. Create a truth table. Document the relation between the gray code inputs and the corresponding binary code outputs. This serves as the reference for the building logical equation. Boolean equation. Derive Boolean equation. Use the truth table to develop Boolean expression for each bit of binary code in terms of the gray code inputs bits, implementing XOR gates to represent executive OR operation. Adware description language. Choose an HDL. Select an adware description language such as VHDL or Verilog for implementation. Code implementation. Write the code. Implement the gray to binary code converter using the chosen HDL. The provided Verilog example in a previous response serves as the starting point. Test bench design. Create a test bench. Develop a test bench to verify the functionality of your design. Provide various gray code inputs and check the corresponding binary outputs. Stimulation. Stimulate the design using stimulation. Looks like models to stimulate the behavior of your converter. Ensure that the output matches expectations for different input scenarios. Functional verification. Verify functionality. Confirm that the gray to binary code converter meets the specified requirements and provides correct outputs for all valid inputs. Synthesis and implementation. Synthesis the design. If you plan to implement the design on the FPGA or ASIC, perform synthesis to convert the HDL code into a netlist suitable for the target technologies. Timing analysis. Conduct timing analysis if required. Analysis the timing characteristics of your design to ensure it meets the requirement performance constants. Documentation. Document the design. Create a comparative documentation including the design specification, implementation details, simulation result, and any relevant notes. Review and optimization. Review this design. Conduct a true review of the design, looking for opportunity to optimize performance, reduce resources usage, or improve readability. Revision and iteration. Revise and iterate based on the review feedback. Make necessary revisions and iterate through the design process until all the requirements are met.
Hello everyone, I am Annapurneshwari and we are back with a new project that is gray to binary converter. So this is the code to convert a gray code to a binary code, and this is the circuit diagram where we have used three XOR gates. So let us go to the result part. Stimulation and testing. To verify the functionality of a gray to binary code converter, a test bench provides a Verilog code. The test bench initializes the converter module and supplies different gray code inputs. The stimulation progress through each input and the resulting binary output are observed. Understanding the stimulation. Initial state. Stimulation start with the gray code input set to 000. Transition. The gray code input transition through different values and the corresponding binary outputs are computed based on the converter logic. Observation. The waveform viewer in a model sim allows for an observation of a signal transition and the relationship between gray code input and binary output over time. Analysis and customization. Logic explanation. The XOR operations are fundamental to the converter functionality, ensuring that binary output reflects the gray code input. Bitwise transformation. Understanding how each bit of the binary output is derived from the gray code input provides insight into a converter inner working. Waveform transitions. Analyzes the waveform transitions to verify that the gray to binary conversion is happening currently. Pay attention to the points in a time where binary output changes and ensure it aligns with the accept binary value. Sign value. If you read the actual sign value at a specific time points by over the waveform, verify that the binary output correspond to correct conversion from gray code inputs. Stimulation duration. Ensure that stimulation duration is sufficient to cover all relevant test cases and transitions in your design. Adjust the stimulation time if necessary to capture the complete behavior of your converter. Debugging. If there are any unaccepted results, use the waveform viewer for debugging. The waveform viewer will display a timeline with a waveform representing the binary output for each set of gray code input. You inspect the stimulation result and verify if the gray to binary conversion is behaving as expected of your test cases. And this is the required output, where we will give force and we will give value as 1010, and this is the required waveform we should get.
Hello everyone, I am Bhagyashree. Now I am going to explain conclusion of the gray to binary converter code. The conclusion, the mini project aimed to design and implement a Verilog code for computing the gray to binary converter. The project's objectives were successfully achieved and implementation demonstrated proficiency in digital design principles. Verilog programming and practical application of the gray to binary operation. The following key conclusion can be drawn for the mini project. First one, successful implementation. The Verilog code effectively computes the gray to binary converter through rigorous testing and simulation. The correctness of the implementation has been validated for a wide range of input values. Scalability and adaptability. The implementation exhibits scalability, allowing for easy adaptation to different input sizes. The use of the signed data type ensures the versatility of the code in handling both positive and negative numbers. Efficiency and resource utilization. The Verilog code is designed with an emphasis of efficiency and resource utilization. Through optimization, the implementation minimizes hardware resources usage while maintaining a high level of functionality. Education value. The project serves as an education tool, providing a clear, concise example of the gray to binary converter implementation in Verilog. The code's documentation and structure contribute to its suitability for learners in the field of digital design. Readability and documentation. The Verilog code prioritizes readability with meaningful variable names, comments, and a well-structured format. The accompanying documentation offers a comprehensive overview, aiding in understanding and potential future modifications. Simulation and testing rigor. Rigorous simulation and testing were conducted, converting various scenarios and edge cases. The project's success in handling different inputs and producing accurate results enhances its reliability. Real-world applicability. The implementation showcases the real-world applicability of the binary gray to binary operation, particularly in scenarios where signed arithmetic is essential, such as processor design, data representation, and error detection mechanisms. Future consideration. While the current implementation meets the project's objectives, there is a potential for future enhancements. This may include further optimization, additional features, or integration into more complex digital systems. In conclusion, the Verilog code for implementing the gray to binary converter has successfully met its objectives, providing a valuable contribution to digital design understanding. The project's emphasis on correctness, efficiency, and educational value positions it as a solid foundation for the further exploration and application in digital design context. Thank you.